I'm Ben Kopp from Emory University. Glad to be here. I'm joined by my co-chair, Lael Yonker from Mass General. So we're excited. I hope everybody has some energy left for this last session. We don't have any relevant disclosures. Maybe the slides will advance too. Okay. Yeah. So this is a kind of an emerging session. So we're hoping to really talk about some new concepts and immune dysfunction in CF and really think about the changing landscape and how we're still faced with persistent inflammation and immune dysregulation, even in the context of highly effective modulators. So we have some great talks today thinking about autoinflammation and autoantibodies in CF, thinking about the effects of resolvins and resolution of inflammation, thinking about new approaches to immune modulation in CF, which is not something that we've really done so much today. And over the whole course of this, really thinking about how aging impacts disease in CF and particularly the immune system. So we have a fantastic lineup of speakers, which are shown here. So we're excited that they can all contribute today. And then we were going to have a question and answer panel at the end, but we're going to just do questions at the end of each talk. Dr. Crick has to leave right after her talk, so we're going to do these individually. So with that, I'll turn it over to Lael.
Great. So first speaker is Balaz Rada from the University of Georgia, and he's a really accomplished and talented researcher who's been studying neutrophil biology in the laboratory of neutrophil biology and mucosal innate immunity. And his talk is Association of Staphylococcal aureus with Systemic Autoantibody Signatures in CF.
Thank you.
Yes. All right. Is it working?
Okay. So I'm not going to shout. So thank you very much for the chairs to invite me. It's an honor to present here our findings related to autoantibodies in cystic fibrosis. I have nothing to disclose. So I wanted to start the talk with the classical triad of CF lung disease when you consider that mucociliary clearance is impaired. You have inflammation driven partially by neutrophils or mainly by neutrophils and infections. And we wanted to study whether autoimmunity could be part of the landscape. We think that the conditions are given. Chronic inflammatory conditions many times come with exposure of the autoantigens overriding the immunotolerance. The standby effect is there to the microbial infections, so CF wouldn't be that surprising if actually autoimmune symptoms are there. And so autoimmunity, just to make sure everyone is on the same page, it's specific to the adaptive immune response, that the adaptive immune response attacks the host. And this comes in principally two forms. You have autoreactive B cells and plasma cells that make autoantibodies, or autoreactive T cells, and the two major branches of the lymphocyte response. And if you look at the literature, there have actually been quite a few papers in PubMed showing that autoantibodies have been detected in CF patients going back to even the last century, the 1990s and earlier. And their targets were all neutrophil related. So myeloperoxidase, BPI, proteinase 3, azulosidine, and even a modification of post-translational modification called carbamylation that has been described to occur during NAT formation. Autoantibodies targeting it were described in CF. So there's some presence in the literature for the existence of autoantibodies, but that's pretty much when it stops in terms of our understanding. So my lab at UGA in the last 10, 11 years has been studying neutrophils and neutrophil extracellular trap formation. One of the projects studied NATs in CF, and NATs occur in CF airways and could serve definitely as a primary platform to deliver several autoantigens to the airways. And we wanted to ask whether other components of NATs that haven't been studied yet could be detected in terms of autoantibodies are produced against them. And one of the obvious choices is DNA. Extracellular DNA is DNA shouldn't be out there in the extracellular space, and if you have autoantibodies produced against it, it's a problem. For instance, in lupus, it's a signature autoantibody. Histones, PAD4 is an enzyme which mediates one form of the NET formation, and autoantibodies against PAD4 or autoantibodies against the products of PAD4 activity, which is citrullination of proteins, including histones, have been described in rheumatoid arthritis. So this is a collaboration. Everything I show you, it's a collaboration with the Emory CF Center. And I've been blessed having, again, Emory and next door. And this was helped since the beginning by Arlene Stachenko and the CF Biorepository, because at UGO we don't have access to clinical samples pretty much to CF patients. So this project on exploring autoantibodies in CF started with 37 CF patients. These are adult patients. We had healthy controls recruited at UGA. And I also reached out to get serum samples from collaborators who work on well-described autoimmune diseases as references to RA and systemic lupus erythematosus, or SLE. And these were all serum samples. So we are studying the systemic autoantibody response. And first, we just looked for whether cell-free DNA can be detected in the blood of CF patients. We didn't find any difference between the CF and the healthy controls. We measured NATs with an ELISA that measures neutrophil elastase DNA complexes. And again, we didn't find any increase of NAT levels in the CF serum. But when we looked at nucleosome antibodies, again, with lupus, we get, as a reference disease, we get higher numbers, but in CF, we didn't get any increased levels of anti-nucleosome antibodies. And ECPAS, which are anti-citrulinated protein antibodies, autoantibodies, which are characteristic in a subpopulation of RA patients, in CF, they did not show any elevated levels. So, however, when we looked at for anti-PAD4 autoantibody levels, we saw increased levels of these autoantibodies in the blood of CF patients, and serum levels of these autoantibodies also correlated with lung disease, surprisingly. And when we switched, or when we separated CF patients to Pseudomonas aeruginosa positive and negative, there was a higher blood levels of PAD4 autoantibodies in the blood of the Pseudomonas positive patients. So then this project continued on with the involvement of Rachel Lineman at Emory. She had she coordinated a unique cohort of CF teenagers and even children. So we got an extended set of blood samples from Emory, including, again, children and teenagers. And we looked further into details of the PAD4 autoantibody levels in their blood. And what we found on the left side of the slide, you can see that in adult CF patients, we confirmed with the larger patient numbers that the PAD4 autoantibody levels are higher than in healthy controls. On the right side, which was more newer information, that in teenager people with CF, we found, again, elevated levels between 10 and 19 years of age compared to the age-matched cohort indicated in purple on the right side. For CF children on the left side in red, their levels was also elevated, but we didn't have at that time age-matched controls, but the higher level in compared to the healthy teenagers, again, suggests that this autoantibody response might be going on relatively early in life. The correlation, there was also a confirmed correlation between age of the CF patients and also the PAD4 serum blood levels on the left side, and also the PAD4 antibody levels correlated with lung disease, as you can show it on the right side. And this is, again, close to 100 samples. After this, we left PAD4 autoantibodies behind, and we went out to explore whether DNA autoantibodies, which, again, have been described in lupus, and their signature autoantibodies in lupus driving pathogenesis, are present in CF patients. Wouldn't be that surprising, since we know that the areas of the CF patients have tons of extracellular DNA for years and decades of their life. So the antigen is there to potentially trigger an adaptive immune response. Here, in this study, we use different populations of CF blood samples. We will use, here I will show you data from the publication which are belong to the CF2 and CF3 cohorts. And when we tested for double-stranded DNA autoantibodies of the IgA subclass, we found higher blood levels of them in CF blood, and the IgG class were not significant or wasn't different in CF patients. So this was interesting that people typically look for IgG as like a baseline type of autoantibody, but since CF airway disease is a mucosal, inflammatory infectious conditions, and IgA is the prominent class at the mucosal sites. So it could make sense that you will have also IgA antibodies produced against autoantigens in CF, people with CF. Why is it in the blood? I mean, that's an indication that it could be plasma cells who went back to the bone marrow or hide in the mucosa. It requires further exploration, but definitely it was interesting to detect double-stranded DNA IgA autoantibodies in people with CF. But we also found that the levels of these double-stranded DNA autoantibody, IgA autoantibodies, correlated with lung disease again in this cohort. So similar to the PAD4 autoantibody levels. This is just another way of showing it. When you group the people with CF into low and high group in terms of autoantibody levels, the FEV1 values are significantly different. However, in this case, we had no association to the airway infection. No correlation with Pseudomonas or staph infection was observable. And when we also looked at along the age of the people with CF, there was again a correlation in the serum double-stranded DNA autoantibody levels between age. And on the right side, as you can see, we had healthy cohorts again from adolescent patients and adults, and there were the levels in the people with CF were higher, significantly higher than in the age-matched healthy controls. So after having described two new autoantibodies in CF, it's going to take some time until you test one autoantibody after the other. Plus, commercial kits are actually pretty rare. There are not many available to study these. So we decided to try to have a more exploratory, unbiased approach. And I found publications from a group back then at UT Southwestern on using an autoantibody microarray. So it's pretty much a protein chip. They spot proteins, the antigens, autoantigens on the array. You can apply 50 microliter serum, and they are adding the secondary anti-IgG, E or secondary antibodies, and you get a fluorescent heat map, and it's a really good, more unbiased approach to study the autoantibody landscape than just testing one autoantibody by ELISA. And this was done by Kwanza and Lee, who we've been collaborating since. This goes back to several years by now. So using this autoantibody microarray, you can spot close to 120 different autoantigens. Back then, they only had a limited set of pre-made chips, but now he's working actually for a company in Maryland. They have now several options to approach this. And back then, I requested, I worked with him to have a custom-built autoantigen panel. I didn't like exactly whatever they had to offer back then. So these autoantigens are pre-selected. Some of them are neutrophil markers, some are markers of tissue damage, some of the cytokines, and of course, autoantigens for well-known autoimmune diseases are also included. I also asked them to have a non-citrullinated version and a citrullinated version of these proteins, autoantigens, because again, protein citrullination it's happening in CF airways and again could trigger an autoimmune response. These are the results we get of the 8 different microarrays. This is just the heat maps to show you. Again, the upper row shows you the non-citrullinated antigens against the 4 major IgG classes, and the bottom row is the citrullinated antigens. The conclusions or the results of this study was that in the upper row, again, you see we came up with this total autoimmune score, which pretty much for each patient, we added up all the fluorescence belonging to the 120 autoantigens, and we said that's the closest approximation in our case to measure the autoimmune response, autoimmunity. And if you did that for a total IgG or the separate IgG classes, pretty much we saw no significant difference between CF and healthy controls. So that would mean that CF patients, at least against these 120 autoantigens, don't really have an overall really large bias in the autoimmune response. Of note is that the controls of RA, for instance, the citrullinated antibodies, they were higher, so that's an indication that our reference controls worked. Again, RA patients, they have higher levels of IgM and IgG against citrullinated histones and proteins. So when you look at we graph this volcano plot, which shows you the ratio between the CF patients and healthy controls on the x-axis and the p-values on the y-axis. For each subclass, you saw different red dots above the significance line, meaning that certain autoantibodies in this cohort were higher in CF or lower in CF. So this is, for instance, just showing you the IgG levels. 2 we found to be higher in CF and at least 8 or 10 lower in CF patients. IgM was also, we had, I think, 4 or 5 hits, and 2 which were lower, and the same for IgA. And in the interesting thing with IgA was, again, that all of them were higher in CF patients, and that half of them, the levels in the blood, they correlated with lung disease. We had the FEV1 values from these patients. So it's this is here shown for individual IgA autoantibody scores on the x-axis for each of those indicated in the orange brackets in the table. So those are the autoantibodies whose levels, based on the microarray, are correlating with lung disease in CF patients. Then we correlated these with several parameters of CF patients. And we had certain antibodies which were associated with Pseudomonas infection. We found really nice, some interesting correlation with CF-related diabetes and the IgA signature. But here, I'm only showing, I wanted to focus on the infection. So we found an interesting autoantibody signature between staph infection in CF patients and IgM autoantibodies. On this scale, as you see on the left side, again, each dot is a patient, and we grouped CF patients into staph negative and positive populations. So the staph negatives are the purple, staph positives are the red, and the healthy controls are the blue. And IgG, IgM, and IgA are the 3 graphs. And only for IgM, you see that this autoantibody score per patient is higher in staph negative people with CF. You don't see a significant difference between in IgG and IgA levels. And when you, again, present this volcano plot, you see that, I think I put a quadrat on that you see that that almost half of the IgM autoantibodies were significantly lower in a staph negative patient. This could be, of course, given some bias from the age or the lung disease, but in our cohorts, the staph negative and staph positive people with CF had no significant difference in age or their lung function. So I think there's a likelihood is less that this is caused by the potential differences in the age or lung disease. And so we found the top 7 hits of IgM autoantibodies that were higher in staph negative CF patients. We also found relatively weak but still significant correlation between lung disease and IgM autoantibody score in the staph positive CF population. And this correlation was absent in the staph negative cohort. These were the top autoantibodies of IgM whose levels correlated with lung disease in the staph positive population. So again, these are really interesting correlations, as you can see. So at the next step, it's great to have one cohort, but we try to make some big statements about autoimmunity in CF. We have to use more samples, and then I try to reach out to another CF collaborator. I'm from Hungary, so I've known Béla for a while, and they also work with CF patients in the city in eastern Hungary called Debrecen. And I got serum samples also from him a while ago. And here you see the CF cohort and the healthy age and gender-matched healthy cohort. And we did pretty much the same. We subjected these serum samples to the microarray. We did not use citrullinated autoantigens based on the Emory cohort. It seemed like there's no difference. There's no role of citrullation in autoimmunity in CF based on our data. First, we wanted to confirm what we saw before. In the Emory cohort, that the double-stranded DNA Ig and the PAD4 antibody levels are higher. And we found also in the Hungarian cohort, indeed, that significantly higher blood levels of these two autoantibodies. So this is reassuring that if you see this in two cohorts, that's most likely true for the whole disease population. We did again the same. We used the serum samples were matched, and different numbers were applied, and these are the heat maps. I have to say that this is a different panel of autoantigens than the first one, so there are differences between those 100, 120. This time we used the pre-made panel by the company. It's an inflammatory panel. And so, again, this could be a reason for potential differences. In the overall systemic autoantibody landscape, again in CF, we saw pretty much the same, what we saw in the Emory cohort, that there was no difference in a total autoantibody score, or even if when you split it into IgG, IgM, Ig, or even the IgE. So that's confirmed between the two cohorts. We again saw a few autoantibodies that were significantly higher or lower, and the pattern looked very similar to the first cohort. The question was what happens with the observation we made in the first cohort with staff. And luckily we could reproduce it, meaning that there was again half of the autoantibodies, which are IgM, they had a lower level in staph negative patients versus the staph positive ones. Interestingly here, IgA showed a similar pattern, and we did not see that in the Emory cohort. So that's the reason for this could be several, but this is again, this is different between the two cohorts. And when the total IgM score was again calculated, we again saw that, going back one, in the middle graph shows you again that the staph negative CF, people with CF had significantly higher total IgM score, autoantibody score than the staph positive ones. Correlation with lung disease was not reproducible here. Clearly, as compared to the first cohort, so there was no correlation significantly between lung function and the total IgM score in staph negative or positive patients. So overall, that's how far we analyzed the second cohort. We still have to make more progress with it, but the conclusions are here listed on the slide. So we detected several autoantibodies that are higher in the CF blood compared to healthy controls based on microarray data. Very interestingly, most of them could be, they are either components of neutrophils or could be linked to neutrophil-mediated tissue damage. There's a lot of, several collagens were on the targets and so on. So I think that's how we can link inflammation to autoimmunity. With ELISA, using two independent cohorts, we confirmed the double-stranded DNA and PAD4 autoantibodies to be higher in CF. The nucleosome antibodies and the ACPAS were not different. We suggested several associations of autoantibody levels and signatures with clinical features of CF patients. And especially for staph, after two cohorts, it seems really reproducible that for some reason, staph infections correlate with low total IgM autoantibody levels. There are limitations to this study, like most of studies, so the number of people with CF was relatively small, so that's something to consider and to work on. Even if we applied 120 autoantigens on a panel, this is only a snapshot of potential several thousand autoantigens. So by selecting these, you might have an inherent bias in what you're looking at. We need to confirm several of these data with secondary assays. Unfortunately, commercial ELISA kits to detect autoantibodies are actually not so common. The only ones you can buy is actually against autoantigens, which are already known autoantigens in autoimmune diseases. But that's it. Several of their hits. We have to make a homemade ELISA or look for some other confirmations, and of course we have to keep expanding potentially more CF centers to make a pretty general statement about autoimmunity. However, acknowledging that correlations are not causation, it's definitely a possibility that somehow there is a causative interaction between the antibodies and staph infection. And it could suggest, this data suggests, if there is a link between them, that these are actually, there could be beneficial IgM autoantibodies helping staph clearance in the CF areas. And IgM is the main antibody to activate the complement system on bacteria. So it's really important for opsonization and then labeling the bacteria for phagocytic uptake. Gram-positive like staph are not really easily being killed by the complement system alone, but again, the activation by IgM is really important for potentially label them for phagocytes. Staph, actually, I looked in the literature, is known to cover itself with host proteins and getting several publications which and those proteins are overlapping with our autoantibody targets. So we have a really exciting, interesting, completely theoretical hypothesis that staph tries to trick the immune system by covering itself with host proteins, so anti-staph antibodies would not recognize it, and it would avoid recognition by phagocytes. At the same time, if people with CF have certain autoantibodies already, and they are targeting those proteins that staph uses to cover itself, actually this strategy might backfire for staph, and those autoantibodies might actually serve as opsonins for staph or phagocytes. So this is just one example, again, completely unproven, and we will try to work on this, how autoimmunity could bias the immune response in patient populations, including CF. We'll also try to look into definitely the mucosal autoimmune landscape, so studying sputum or BAL samples, because with the company said we can do the same thing with sputum samples, so definitely where the lung disease is happening is a little bit more direct approach than the blood. So with that, I would like to thank funding by NIH and the CF Foundation, my lab members, of course, Emily, Arlene, and Rachel, Quan at the company, Bela at Debrecen, and of course the two University of Alabama. Louis, he's moved to, I think, University of Michigan by now, who worked on RA, and Michelle Kallenberg at University of Michigan, who provided all the lupus samples. Thank you very much. I'm happy to take any questions.
Thank you. That's a very nice talk. And I think it's really interesting about the separation of staph in CF patients as staph negative or staph positive. I don't know if I missed it, but did you include gender as a variable to pull out if antibodies were different in CF males or females?
Yes, so we, in the first approach, not, but then we did a multiple linear regression analysis, and we also included several other variables, and the gender was included, and it still remains significant, yeah.
It was significant.
It was significant between the staph negative and positive population.
But what about between male and female?
Oh, you mean separating the CF patient, looking at this? I can look at it. I don't think we have done it, but I'm afraid that the N will be even lower with total. We have 30 plus a few people with CF, so we will definitely look at it. But I'm afraid that we need more samples.
We did a sample of 104.
Oh, the big one, right?
Large sample of 104. There's still between genders.
Okay.
Yeah. Okay.
Thank you.
So questions can be addressed to Arlene as well.
Nice work, Belis. So I have a question. Would the bacteria double-strand DNA stimulate antibody production as well?
Definitely. I mean, staph antibodies have been described, and Pseudomonas antibodies are out in CF patients. So this microarray focuses on autoantibodies by the fact that the company spots host proteins. They actually now started offering also microbial, I think they have a COVID panel now. So it would be interesting to look into that. And we have to also look into the total antibody levels, because the fact for me that, for instance, half of the IgM antibodies show a pattern that tells me that the antigen is really not that important. It's something that with the IgM mechanism, and IgM especially, I just made a note, it's actually most natural antibodies are IgM, so they can make it in a T-cell independent manner. So there's B1 B cells, the naive B cells. So I think that's the most likely is going on, that somehow the IgM production for whatever reason, some of them are even there before the infection. So I think that's the most likely mechanism, but adaptive immunity, to study it on trying to get competitive national funding is new to me, so I'm definitely learning about it after innate immunity. But it's a 5x in our efforts in terms of trying to understand which one do we do it first. But I agree. Going back to a question, like the bacteria definitely trigger antibody production, so we have to look into that.
All right, thank you.
Hi, nice talk. Really like the IgM part. So on that thing, do you know if these are new antibodies, like new infections, or is somewhat they're not going the isotype class switch to another IgA or IgG?
We don't know. This is, again, just based on the secondary antibody, what they use on the arrays, so we have no information about that. So it's completely theoretical, again, that again, based on the literature I'm reading, my favorite hypothesis is that these are actually natural IgM antibodies. They haven't undergone the class switch, and most likely these are these B1 B cells, the non-classical B cells, not the B2 cells would make them. That's my a favorite hypothesis. Those IgMs have low affinity against the antigens, but since they are pentamer, they actually have a higher avidity. So, but we have to look into all these. And again, there's zero autoimmune model in CF. We are testing now mice, and maybe so. There's a lot to work to do to try to. The next step is to show these antibodies do matter. Do they cause pathology, or are they pathogenic or beneficial? Because if we can show that, even healthy, the patient population, like 10-20% of healthy people walk around without antibodies, without any clinical consequences. So that will be more hard. We try to isolate them. You can't purchase them. So we are facing a lot of new things, but hopefully we'll get to the next level.
Thank you.
All right, last question.
Hi, Robert Gray from Glasgow.
Hi.
Great talk. This is probably a naive question, but I'm just wondering, have you looked at complement activation in response to your high antibody levels? It's just in other inflammatory diseases, complement activation as a target, as an anti-inflammatory. So
yeah, so definitely we were thinking about that, and actually C1q was one of our hits, and I think it was an IgM, which is one of the complement marker for the immune complex mediated version of the complement activation. So we haven't looked at it. Right now, we are trying to group staph negative and positive sputum and blood samples and try to run the microarrays and try to do something. The problem is we need isolated antibody to use it as a reagent. And for instance, again, like we've been spending 2 years reaching out companies and academic. Antibodies are well protected. No one wants to share them, or it's really so pretty much we don't have. Let's say if I want to have an anti-PCNA IgM, which was our top target and hit, there's nothing on the market. So we don't have to make it. A mouse is all the questions. I would love to prefer a human or a rat. So we have technical difficulties in getting the reagent. But I would love, because after that, it would be really easy just to add the antibody and measure complement activation. But we are facing the problem of the reagents at this point.
thanks.
Great, thanks so much, Balaz. And sounds like a round of applause. And if people have samples that they want to share with Balaz to expand his cohorts and ask about post-Trikafta effect, that would be really interesting. So, thank you.
Yeah, I think we actually have some for you for that. So, all right. Well, next up, we'd like to welcome Dr. Stephanie Crick to the microphone. She's at the Division of Pulmonary and Critical Care Medicine at University of Alabama at Birmingham. So she's going to give us a nice perspective from the adult side on the effects of aging and immunity in CF. So welcome.
Thank you. And I move forward.
And so this works best if you do that.
So I click on it.
Looks like that.
Well, thank you very much. Thank you to the organizers for inviting me. And I think I will be a little bit the odd bird here because I'm talking about effects of aging on immunity in cystic fibrosis. and then realized what kind of enormous task that really is. So I didn't generate this data all. I show a little bit of my data, but I'm mainly in airway biology and in aging. So I shamelessly recruited the whole scientific community in aging and in cystic fibrosis, and show, I think, overall like an overview, to kind of give you an overview about like aging in general, and then what has this to do with CF and where we go from here. So please bear with me. I have nothing to disclose. And I think starting with really the future of cystic fibrosis, and I love this slide, and you probably have seen here multiple times already at the conference, is that, and that's why aging always seems to be not fitting with cystic fibrosis, but because post-war, this was like a pediatric disease. You were actually lucky when kids turned 5 years old. But then with all the developments through the CF Foundation and the scientific community, we were able to get better airway clearance measures. We were able to get inhaled antibiotics, better nutrition, pancreatic enzymes. That life expectancy really increased significantly. And now, especially with the modulator therapy, we are really at a point where these patients can live their lives fully. And we really have to think about aging, because these patients now, the new life expectancy is in the 60s, and projected actually now when kids start with Trikafta at 2 could be in the 80s. So this is really something we need to think about. Looking here again at the prevalence of respiratory organisms in people with CF, same thing. This is a slide I think everyone has seen here also multiple times and before, but it really ends at 45, right? So what really happens after 45? This is something, it's completely like we are in no man's land. We really don't know. And that's something we really have to start now thinking about. And I want to step back and really look at the aging lung and introduce some of those concepts. The aging lung, and this is healthy aging, physiological aging, we call it, changes. And with age, you have increased airway spaces, which is also called senile emphysema. You have more in the cells don't proliferate that much anymore. There's more apoptosis. You will see general less elasticity, and there's a chronic inflammation going on. And this diagram here shows what you see when patients age healthy. There's a line that shows vital capacity of the lung when it comes to disability. And normally when your lung matures, and maturity is really at age 25 and plateaus, and then you age in a healthy way, you should never reach that disability level. But there are diseases, classic diseases like IPF, for example, which is a known disease of age, when these patients' lung maturation takes place and fully, but then you have this accelerated aging happens and lung function decreases. And I think in cystic fibrosis, we don't even, or we at least didn't used to reach that plateau at all, because the kids are born already with CFTR dysfunction, and then they don't mature fully. And then again, you decline your vital capacity even more. And that's what we really have been dealing with. So going even a level deeper is Dr. Lopez Otin has described that in 2013, and this is not organ specific. This is really all over organs and tissues, the hallmarks of aging on a cellular level, an intercellular level. And there are 10 hallmarks that he described, including genomic instability, telomere attrition, epigenetic alteration, loss of proteostasis, then deregulated nutrient sensing, mitochondrial dysfunction, which has a lot to do with a reactive oxygen species and generation, cellular senescence, which I'm very interested in, stem cell exhaustion, and I should have brought myself because I don't see that here, and altered intracellular communication. So this was all well described. Again, this is not lung specific. And then in 2015, Silke Meiners actually talked about the hallmarks of the aging lung. And they are the same 9 hallmarks, but what she showed is that extracellular matrix dysregulation also plays a big role. And coming back again, aside from cystic fibrosis, the poster child of age-related lung disease is really IPF. And that's what you really see a lot there. So she described it mainly for COPD, which we also know as aging-related, and IPF. And so the question always was then, what about cystic fibrosis? Because we have chronic inflammation going on. And when I started my faculty position at UAB, I started thinking about that and got kind of really pitied in like, what am I really thinking? Because it doesn't play any role, right? How could you even think about that? So then COVID hit. We had lockdown of the labs. My students were really bored. And what we said, let's just do a review on it and look at evidence of accelerated aging in cystic fibrosis. And I apologize for the busy slide, but there are all those 10 hallmarks listed. And there is actually a lot of evidence when you look at it. There is in blue, this is more controversial, stem cell exhaustion and telomere attrition. There are like findings pro, but also findings con. The green one, there is some evidence, but all the ones written in yellow, there is some evidence there that there seems to be activation of aging in cystic fibrosis. So picking some of those, for example, epigenetic alterations. There are publications on methylation changes at multiple CpG dinucleotides in nasal epithelial cells and whole blood and lung macrophages of like CF patients. If you, like I talked about the ECM dysregulation, like the 10th hallmark that was added for the lung, it has been shown in CF that neutrophil-derived proteases are the main driving force of lung injury, and that sputum neutrophil elastase correlates with FEV1. When you look at altered cellular communication, there are increased NF-kappa B inflammatory mediators. There is increased neutrophil recruitment, which we all know. We have plenty of literature. And there's also a decreased response to interferon gamma. But coming back now to the immune response overall, when we look at age. And I love this publication, which is way back in 2013, because they really call that the immune response created a salutary environment back when it's healthy, which means you have a lot of diversity of B cells, of T cells, CD8 and CD4 cells, and almost comparing it to like a young dog that is fresh, jumping around, and has the whole repertoire. When we age, it turns into an inflammatory environment. Basically, a dog that is 10 or 15, the right breed, and doesn't really want to play anymore, right? So now we have really monotony. There is reduced antibody generation or antibody avidity when it comes to B cells. And it's same with the the T cells. They are more Th17 cells. And it's normally, there's just less fluidity there. When you look at aging and tissues in immunity, aside from the lung, and we all know that, I think, that the thymus, that it involutes when we age. The bone marrow, I think coming back even to one of the plenaries, if you were there with sickle cell disease, that it's hard to really work with the bone marrow of older sickle cell patients, that strategies don't work because same thing, it gets replaced by adipose tissue. And the spleen, the lymph nodes, same thing. There is like a decrease in active cells, there's more inflammation. And when it comes to the lung, same thing. The lung, we have like more inflammatory cells that are now residing in the lungs. If we look at the innate immune phenotype of the aged lung, and here the author actually looked at aged healthy conditions, where this aged after infection could show that this anti-inflammatory macrophage phenotype that was very domineering in the aged healthy condition actually is substituted more by an pro-inflammatory phenotype. And the anti-inflammatory phenotype really decreases, and there is more neutrophil. There are more neutrophils. But now coming back to cystic fibrosis, how about immunity in cystic fibrosis? And what I will focus on, like I said, I'm already recruited a lot of the scientific community, and there is more, but I really want to focus more on these 5 cells, on the epithelial cells, on the neutrophil, on the lymphocytes, on the macrophage, and the dendritic cells, who all interplay. And here as an example with Pseudomonas infection. So what do we know? And this goes really far back. Immunity in patients with cystic fibrosis. And it's really described more as a hyperinflammatory response, which early on, for example, there was a very old study on hypogammaglobulinemia in patients with cystic fibrosis that were less than 10 years, and this was associated with less severe lung disease. And also what was shown that if patients are infected with Pseudomonas or Aspergillus fumigatus, there is an increase in neutrophil chemoattractance or an hyper-IgE-like state that is domineering in CF. This is, again, going really far back, hypothesis about primary and secondary effects of the innate host defense system in the CF lung. There's one, which is this isotonic volume transport mucus clearance hypothesis, which links CFTR dysfunction and airway infection directly. Whereas in the other one, it's hypotonic airway surface antimicrobial substance hypothesis, where it seems that the CFTR defect leads to elevated salt concentration that inactivates antimicrobial substances. And then the CFTR deficiency itself causes abnormalities in cell biology of the respiratory epithelium, and that interferes with host defense. So it's very complex. Coming back to the cell types, though, and looking at CFTR dysfunction in neutrophils, for example, what has been shown in CF is that neutrophils have a reduced phagocytotic capacity. And also there is a defect in its respiratory burst, and that seems to attribute to disrupted chloride transport to the phagolysosome. The CF mast cells have increased interleukin-6 levels, and that also affects regulatory T cells. And then it has been shown in another study that CFTR mutation, just the mutation itself, affects approximately 89 genes of these neutrophils. Here an example, and thankfully Camilla is actually in the audience. This is just one example of how CF airway neutrophils behave. And this is, she's done in her publication back in 2021, looking really at the transcriptional adaptation when these neutrophils migrate through the airway epithelium. And that the transcriptome changes, and there's a high degranulation and a low bacterial killing. But when she used then transcription inhibitors, that she could actually attenuate this. What we've done, and like I said, I only show a small portion of that. We mainly focused on the bronchial epithelium. And we did that in collaboration with Dr. Burkett at UAB and looked at the CFTR knockout rat, where we could show that cell senescence is evident in the bronchial epithelium of those rats, where we see increased expression of P21, P16, which are markers of cell cycle arrest, BCLXL, which is a marker for apoptotic resistance. We showed increased beta-gall staining, which is a lysosomal marker of cell senescence. And down here you see the SASP markers, which are senescence, the senescence-associated secretory phenotype, which are pro-inflammatory mediators that normally secreted and are part of like the cell senescence. We've also shown that in primary bronchial epithelial cells from CF patients, and have been working now on potential underlying mechanisms. If you look at lymphocytes in CF, this seems to be prominently a T2-mediated disease with high interleukin-4 and interleukin-13 release. And as I showed before in aging, also here it seems there's a high involvement of Th17 cells. There's a reduction in natural killer cells, and it seems that invariant natural killer cells play a role. And if you delete those, you can actually attenuate lung inflammation, which has been shown in CF mice. And there is a reduced telomere length in leukocytes, and that is associated with severity or disease severity in CF patients. When it comes to dendritic cells, the same. I think the common theme, what we've also seen in aging, is that we have less diversity. So there seems to be the total number that is decreased, but there's also seems to be less expression of CD40 and CD86. And this seems to be regulated through sphingosine-1 phosphate. And there's also a delayed differentiation, which has been shown through the decreased expression of caveolin-1 and abnormal regulation of lipid metabolism. Looking at macrophages, and I know there we have a lot of expert of macrophages here, when you look at the CF pig, for example, you see also a pro-inflammatory response. But they also, same thing, we have less diversity. They seem to be stuck in the M1 phenotype. And this way it's hard to resolve inflammation. And they don't respond appropriately to the environmental stimuli. So they're also defective in autophagy, efferocytosis, and interleukin-16 regulation. And I think the big question is now, where there's really not much known at this point, and I know this is coming later in the session, is what about CFTR modulator therapy on immunity in CF? Does that change things? There are some reports that shows, although we really see this increase in lung function in a lot of patients, improving in sweat chloride and improvement in mucociliary clearance, there is still chronic inflammation going on. And our paper right now is in revision. We're asked if this plays a role in cell senescence in the bronchial epithelium. And when we treat those cells with Trikafta, the primary cells, we really don't see any change in cell senescence. But there's a really few studies, and I think we need to look closer into that. So summarizing all that, and I apologize for things are left out because this field is really big, but there is evidence of aging-related changes in the CF lung and its innate immunity. And underlying factors are CFTR dysfunction, but also others really play a role, like chronic inflammation and infection. But we really need more studies to develop targets for that. And I think even the bigger question is what I showed you right now is really, I showed you aging phenomena, and I showed you phenomena that happen in CF. But what if these patients are getting old? What we've seen here, most of the data is from 20, 30-year-old CF patients or even younger. What if they, now that they can get older when they turn 60 or 70? What happens here? So that's why I think for me, it's a very interesting field. And I think there's way more to come, also keeping in mind modulator and when modulators are started. So with this, I want to thank everyone for your attention, and mainly also the CF community and CF patients and parents to bear with us and hopefully help develop more strategies to help those patients. Thank you.
Any questions? I can start off sort of airway epithelial sort of integrity with aging. There are some, I'm curious if you've looked at the role of zonulin, which is a tight junction regulator in the airway. And if you've considered that in aging.
We haven't looked at it, but not specifically looked at it, but probably indirectly because we work a lot with ALI cultures and have them on filters. And so there is really no difference in TER when we measure that. And we see these cell senescence markers expressed. I think so cell senescence markers, that has been like a whole ordeal because we show a couple of those, but the field is big. And there are some, I think, some in the research community think, well, you need to show hundreds of those. And that's why it's always very hard what you really or think is the cell senescence marker, what stands for it. So that's why I think it would be neat to look into it, like when we have these cultures, we sometimes have submerged cultures as well. But when you look really at differentiated ALI cultures, there I would think, if it has to do really with tight junctions, there is no difference there.
Robert?
Hi, that was a really amazing overview. I was just wondering about the sort of difference between inflammation that's caused by infection and inflammation that's, innate, the sort of nature, nurture debate. How do you sort of reconcile that with your rat data? Because that looks really interesting. You've got markers of senescence, but I'm assuming there's not a huge amount of infection in the model that you've used.
Yeah, and so that is actually our next step, which I haven't shown here. We started with Pseudomonas infections, mainly looking at Pseudomonas. So the rat is a little bit difficult there because they love to clear it right away. But we're trying to look like at 3 days, which doesn't necessarily fit much, I think, with CF. What we also did, we infected ALI cultures with Pseudomonas and try kind of to drag it out to 24 hours and looking at cell senescence markers. And my student is very unhappy at the moment because they are not upregulated. It actually even seems that they come down. You see this inflammation, and so inflammatory markers are up, interleukin-1 beta, interleukin-6, interleukin-8, but P21, there's a trend, but all the rest, they seem to come down. So I think there's something else going on.
Thanks.
Very nice talk, Stephanie. Katie Heiser at National Jewish Health. So you mentioned that there's other lung diseases that are more hallmark for aging, and I'm not any expert in senescence, but based on your research, are there other diseases out there that we should be considering that will be our guides? Like, is it IPF? Is there a different disease that, as our patients age in CF, based on what you've seen in terms of senescence, that maybe will help us predict what we might be seeing in the future?
So I think that's a really interesting thought. And I just recently thought about it even more, coming to IPF. And IPF is truly the poster child. I think there, really, the community is far ahead when it comes to aging in general, looking also at fibroblasts. So now that our patients are getting older, could they get IPF? And how will that look like? And that's why I feel we have to kind of shift more now to injury and injury repair, regeneration. So I think IPF will probably lead more the way than COPD, which is the other big disease, I think, where we see cell senescence. Also, in a way, I think fibrosis is really a concept, although it's in our name, cystic fibrosis. But I think not that many have really focused on remodeling. And I think that's probably something for the future. One of our pediatricians at UAB is very interested in that. But I think that's probably where we also have to head into and look at this milieu. Speaking of milieu.
And Emmanuel asked a question, but that's such a great transition to our next speaker. So.
Hi, Emanuela Bruscia, Yale University. So, very interesting talk. I just wanted to notify that we actually have done some studies on CF knockout animal models, and when you impose on those animals chronic inflammatory states for weeks, we see that and then you let them recover. CF animal model, and CF animals, they do not repair their lungs. There is a strong signature on TGF-beta. There is all things that you would imagine will overlap with a IPF kind of status, and you see accumulations of there is a lot of airway remodeling. So yeah, definitely, absolutely. And I would like also to point out that that is in the context of not having a bacteria there, we're just inducing inflammation with LPS and no mucus, because the CF knockout animal models are notorious not having a mucus obstruction. So whatever we see in the repair process is definitely something intrinsic that comes with the epithelium and comes with the immune cells, because we have also seen that if we remove some of those inflammatory mediators, you can ameliorate the repair process. So that is really, it sets the stage on what you are just describing, which will be very important in the context of patients with CF.
That is great. Yeah. Thank you.
All right, one last quick question before we let you get to your flight. How does the age of your models impact things? So in terms of the rats and the primary cells, because certainly things that we do in our own models can influence senescence. So
yeah, so that's, I think, where we so with the rats, we work with 6-month-old rats. Just because they develop this muco-obstructive disease, which you don't see with 3 months. The rat is very, very expensive. So we haven't had the chance to kind of let them age to like 18 months, how you would do it with mice. But that's something I think that definitely if we would get that funded by NIH or the CF Foundation, we would love to do that. With patients, I think the same. I think we just need more donors that we can really go by age. But the other idea, I think, is, and that has been shown in the conference as well, it would be really with nasal epithelial cells, which we might have to go and look then more into like younger patients versus older patients.
perfect. Thank you so much.
All right, so we'll invite up our next speaker, Antonio Ricciuti, who comes from Italy, and he is really an expert at looking at inflammatory mediators, specifically resolvins in airway inflammation and cystic fibrosis. And his talk today is residual impairment in inflammation and resolution of CFTR modulator therapy. Thank you.
Good morning, ladies and gentlemen. Thank you to the chairs for this nice introduction. Thank you to the organizers for giving me the opportunity to present here today. It's a big honor for me to speak in front of you about the residual impairment of inflammation and resolution in cystic fibrosis and CFTR modulator therapy. So, this one. Okay. So I have nothing to disclose. So when we think about inflammation and CF, the first thing that that comes in mind is that this is an old fight with a dragon, because as we heard yesterday, for example, during the plenary, inflammation, especially in the lung, destroys lungs, but I would say that destroys lives of people living with CF. It begins early in life and continues throughout their lives, starts and persists even in the absence of detectable infection, and is disproportionate, but more importantly, is incapable of clearing the infection. Of course, neutrophils and macrophages are considered the main offenders of lung inflammatory response in people with CF. And there is data that there is a relationship between the basic defect that leads to CF and the unbalanced immune response. But we have to remind that inflammation is the most natural way that our body uses to signaling that something is not right. Which means what? That inflammation is meant to be a protective response. And I have to pay credit to this, to Janelle, who is a young woman living with CF that gave this featured during the plenary session at the NACFC, the meeting a couple of years ago, which is really the fundamental meaning of acute inflammation. Inflammation that, of course, starts when we have traumas or infection in tissues, but also when we have a disruption of the homeostasis of normal tissue. We just heard about senescence. So the first things that happen when the inflammation starts is that the vascular and the tissues respond by releasing substances such as prostaglandins, PGE2, that leads to edema formation. And then you have another process that is the neutrophil influx, driven by many chemoattractant, including leukotriene before, which is the first and one of the most important chemoattractant for this class of leukocytes. Neutrophils that, of course, are the first line of defense against pathogens or against injuries, and when they congregate into the inflamed site, they start to clear the noxious stimulus. They clear pathogens, they remove debris, they remove the cause of inflammation, leaving the space for monocyte macrophages that normally should not continue inflammation. They should actually initiate the resolution and allow the tissue health to be resumed. So what we've learned in the past years is that this process is not a passive process, but is rather actively regulated by specific substances that our body makes to drive this response. So back to lung inflammation in CF, of course, there are many players that participate in this process. There is mucus, there are bacteria, there are epithelial cells, but also there are the inflammatory cells, the leukocytes that they're many experts and many work demonstrated that there is a dysfunction that is linked between the defect of CFTR and the response of these cells. In our group in Chieti, back in 2000, we also demonstrated that other cell types have a dysfunctional activities, for example, platelets and endothelial cells that also have an important role in regulating the passage, the transmigration of leukocytes and substances from the blood into the inflamed site. Platelets, for example, so Domenico Mattosci in our lab was the first to demonstrate that the lack of CFTR on the surface of platelets makes these cells hyperactivated, but most importantly, it disconnect their normal communication with other leukocytes, such as neutrophils, because when platelets from people with CF, when they interact with neutrophils, neutrophils become more activated and they do not undergo apoptosis, which is an essential process for resolution. Also, Dr. Jonker, very elegantly using this microfluidic chamber model, demonstrated that neutrophils from people with CF have an ultra-swarming capacity, and this is particularly relevant if you take, it would be the red dots on the figure, neutrophils from people that are hospitalized. And Camilla Margaroli from Tiro Vanziam's lab demonstrated that neutrophils in the airways, they have a completely different immunophenotype and transcriptomic asset compared to blood, and which leads to hyperactivation, degranulation, and loss of killing capacity. And this is also true with other cell types, such as in monocyte and macrophages. Monocytes and macrophages that have been characterized very elegantly in this study using single-cell RNA-seq analysis just a few years ago. If you look at the bottom of the figure, you see that compared to non-CF people, the lungs is populated primarily by neutrophils, but also by this population of monocytes that replace the alveolar macrophages that are the sentinel of our lungs, and they are important to maintain and restore homeostasis. And this is really important because these monocytes that replace the macrophages are actually those that can drive neutrophils to come in continuously into the lungs and to damage this organ. And this has been very nicely shown by Dr. Bruscia's lab. So, resolution, as I said, is the natural outcome, the ideal outcome of an acute inflammatory response. And this is an active process mediated by specific chemical substances that are generally recognized as specialized pro-resolving lipid mediators that are produced in a cell tissue-specific manner, but also in a time-specific manner. For instance, neutrophils, when they transmigrate or where they form, they are in the inflamed tissue and they form pus, or when they interact with platelets, they can utilize this essential fatty acid, which is arachidonic acid that we all know as a precursor of prostaglandins and leukotrienes. As I was saying, neutrophils can generate a different class of molecules using different enzymes such as 15-lipoxygenase 15-LOX or 5-lipoxygenase 5-LOX. So here is the structure of lipoxygenase 4. This was the first SPM that was discovered by Charlie Serrans when he was at the Karolinska Institute on Ben Samuelson's lab. But also, neutrophils can use different substrate. For instance, they can use the DHA EPA to generate the E-series resolvins, or macrophages and neutrophils, when they interact each other, or when macrophages switch phenotype, they can use DHA to produce resolving of the D-series, such as RVD1 shown here, or protectins, such as PD1 shown here, or marasin, such as marasin1 shown in this figure. So there is evidence that the lipid metabolism and the production of SPM is somehow impaired or unbalanced compared to people without CF. And this, there is a surplus of pro-inflammatory omega-6 fatty acid, for example. This has been shown many years ago by different groups, especially from the Karolinska Institute, that there is an enhanced release of arachidonic acid and a decreased levels of linoleic acid and DHA in people with CF. And also, many groups have demonstrated there is an insufficient amount of pro-resolving mediators. This has been demonstrated by independent groups many times, including the most recent one that is shown in the bottom by Valerie Urbach's group, where they demonstrated also an interesting dichotomy in the production of SPM between male and females. Okay, so why is this relevant to CF? This is relevant because SPM have many bioactions that are beneficial to regulate the inflammatory response and drive the resolution process. For instance, of course, they stop the neutrophils infiltration and their hyperactivation, but also they activate monocyte macrophages to have a non-further phlogistic phenotype. And to clear by phagocytosis or efferocytosis bacterial, cell debris, apoptotic cells. They also have a role in regulating the immune response, such as T cell maturation, dendritic cell activation, and macrophage polarization. And also have a role in promoting the repair of tissue and maintaining the natural regeneration of the tissue. So based on this, what I just said, the question is if SPM are deficient in CF, can we supplement them? Can we replace this? Can we restore this deficiency? So in my laboratory, we focus on this, and a few years ago, we demonstrated that if we take CFTR knockout mice, these were given us by Alessandra Bragonzi from the San Raffaele Institute in Milan, and when we give Pseudomonas aeruginosa and we let the infection establish for a very long time, like weeks, if we treat these mice with RVD1 for just 2 weeks, 3 times a week, we were able to dampen the burden of infection, as you can see in this graph, but also to bring back the inflammatory response up to what we see in non-CF mice. We also investigated how this molecule can impact the cellular signaling of human cells. For this, we infected primary human macrophages and primary epithelial cells from people with cystic fibrosis, and we analyzed the transcriptomic after infection with Pseudomonas. What we found is that RVD1 is able to dampen the inflammatory signaling, like toll-like signaling, IL-1 signaling, NF-κB signaling, and so on. So more recently, we got interested in understanding the role of resolvins in mucus-driven inflammation. For that, we used the beta-INAC mice that Marcus Mal developed. So these mice have a spontaneous mucus accumulation and dehydration, like people with CF, which stimulates a continuous influx of neutrophils and other leukocytes into the lungs. Interestingly, we found that these mice also have a specific exercise impairment, exercise capacity impairment compared to wild-type age and sex matched littermates. You see that they run less, they run slower, but they consume more energy. So in these mice, when we give RVD1 as a treatment for 2 weeks, 3 times a week, we were able to dampen inflammation in the lungs, which was kind of expected based on what I just said, but also we shifted the phenotype, the exercise capacity impairment, because they returned to the level of wild-type mice. What about the other SPM, for example, RVD2? So for RVD2 and we compared its bioaction to RVD1 in a different infection with a different pathogen, which is methicillin-resistant Staphylococcus aureus. Again, here we established the infection in these mice, let the infection persist for weeks, and start the treatment after the infection was present. And again, we were able to see the same pattern of reduction in infection, as you see in this figure, and total leukocytes and neutrophils. But we saw a different effects on other cell types, for instance, macrophages and lymphocytes. As you can see here, mice treated with RVD1 had a lower number of macrophages and lymphocytes, whereas RVD2 treated mice did not. We also investigated if there was a change in the phenotype of these cells. And of course, we took advantage of the single-cell RNA-seq technology that allows to investigate very deep the immunophenotype. So here is the UMAP representation of the BAL cells that are present in infected mice treated with vehicle or RVD2. You can see that they are the classical, the typical cell population that one would expect in the BAL, like neutrophils, macrophages, B and T cells. But if you see the colors, they are different. For instance, the neutrophils and macrophages, they are very diverse. Now, if we compare the transcriptomic asset of neutrophils, for example, that come from RVD2 treatment to those with vehicle, you see that all the pathways, all the genes related to the inflammatory response, such as pyroptosis, cytokine storm, interleukin signaling, etc., they are all significantly downregulated, as is shown in blue in this heat map, whereas other pathways like glycolysis or IL-10 or P10, they are upregulated, meaning that RVD2, PMN, and macrophages are enriched in pro-resolving function but depleted in pro-inflammatory terms. And this is shown also in a poster that we have here today. So what about CFTR modulators? Do they have an effect on inflammation? This is a very known figure. It's from the GOAL study. I'm happy that Dr. Heiser is also here today. That show very clearly that despite a sustained improvement in FEV1, there is a persistence of inflammation and even a rebound of infection after several months of treatment with ivacaftor. The same Dr. Heiser has shown, however, that ivacaftor is able to modify the transcriptomic profile of blood monocytes in people taking ivacaftor, making them less tolerant. We just heard about the immune aging. And the same was also has been also demonstrated with neutrophils that they become less activated. See all these markers like CD88, CD62L, they're all markers of activation that are significantly different when people start taking ivacaftor. What about the triple combination with Trikafta? The PROMISE study demonstrated that there is a persistence of inflammation and infection after several months of treatment with Trikafta. And this has been strongly corroborated by other two studies. One is this one from Dr. Kopp's group, and the other one is from a group in Germany that also included healthy controls, where they found that there is a trend towards normalization, but not completely. So this means that CFTR modulators, including ETI, has a variable effects of infection, inflammation. However, the triple combination has some cell-specific modification, induce some cell-specific modification. For instance, Dr. Kops just published this very interesting results that tell us that the treatment with DTI is able to reactivate the antibacterial capacity of macrophages. You see here in the graphs, but also in this electron microscopy figure. In the middle, you have a macrophage from a person with CF. You look at how flat and how unresponsive these macrophages are compared to the ones from non-CF patient, and even when they are simulated with Shepacha. But when you give ETI, they start to react even more, although to a less extent. And also, this is true for the efferocytosis, which is the mechanism of clearing apoptotic cells. So to summarize, acute inflammation is a protective response that must resolve and to resume health and homeostasis. CFTR dysfunction can alter directly or indirectly the basic mechanism underlying inflammation, such as leukocyte migration, leukocyte response activation, immune reaction, but also the resolution process, such as SPM biosynthesis. Restoring the endogenous level of SPM reprograms excessive inflammation and reactivates the resolution process. CFTR modulators correct some dysfunction of immune cells that leads to persistent inflammation. However, inflammation infection may persist even when CFTR function is rectified. So in conclusion, that despite groundbreaking advances afforded by CFTR modulator therapies, people with CF may still have some residual impairment of inflammation and resolution, meaning that the influence of CFTR modulators on the resolution mechanism must still be investigated, and new anti-inflammatory, or I would call rather pro-resolutive strategies are still required in the area of CFTR modulators. With that being said, let me thank all the collaborators, especially the people from my group, Giulia Ferri and Matteo Mucci, that are here with me. Domenico Mattoscio is also now has his own group in Chieti, and the collaborators, the physiology group, Matteo Serrano and Feliciano Protasi, who did the physiology study on the beta-ENaC mice, Marcus Mal for giving us the beta-ENaC mice, Dr. Craig Hodge for some CF mice, and Dr. Thiru Van Ziam for giving us instruction on the transmigration model. Thank you all for the attention, and I'm happy to take any question. Thank you.
Go ahead.
Hi, that was a great talk. Robert Gray from Glasgow. I used to work in Edinburgh, so it would be remiss of me not to ask a question about neutrophil apoptosis. So obviously, it's one of the major signals for resolution. How do resolvin levels affect neutrophil apoptosis? And do you think changes in apoptotic phenotypes in neutrophils might be important in resolution of inflammation in CF post-modulator?
Okay, so we don't know about the interplay with the CFTR modulators, but yes, at least it has been demonstrated for some SPM, like for example, lepoxin A4, that it counter-regulates the anti-apoptotic effect of some pro-inflammatory stimulus such as serum amyloid A. Personally, we haven't done any apoptotic-related investigation, but certainly this is something that it would be important to study, especially now that we have this new scenario with the CFTR modulators. Thank you.
Antonio,
Hi.
very nice talk.
Thank you.
My question is actually, like, I was curious if you see, or if you actually analyzed some neutrophils derived from CF patients and you see the same changes, like can you incubate them with RVD1 or RVD2 and see some of the changes that you see in your mice model?
Okay, so we did some in vitro experiment with neutrophils from people with CF. Yes, we do. So, and we measure, for example, two readouts. One is the capability to kill, phagocytosis. I wouldn't say kill, is phagocytosis of Staphylococcus aureus. RVD1 and RVD2 increase the ability to phagocytose. And also we investigated the transmigration across epithelial cells, and this, it recapitulates what we see. So you have, when we treat the neutrophils with RVD1 and D2, basically they migrate less and they are less activated. They have less degranulation marker, less loss of L-selectin. I didn't show you today for the sake of time, but there is a poster, it's number 223. So we can talk maybe in front of the poster if you want later.
Do I have time for another one?
And
would ETI affect the receptors for those aspirins?
Okay, I don't know. We don't know yet. Yeah, that would be another point to study.
Okay, Thank you.
See, but the problem with the CFTR modulator, I'm taking the advantage that Autocop is here because I've studied your paper very carefully, is how long, I mean, should we treat the cells for the people that are taking modulators even after the collection, and for how long, and which dose? Because the literature is very confused about this. So, but I mean, back to the question, yeah, it's something interesting to see if the receptor is regulated.
I'm Carla Ribeiro from UNC Champaign.
I know you are.
First of all, I appreciated very much your talk. I do have a comment, and actually a comment / a question for you. As you perhaps know, there are new concepts are emerging from our studies, and other studies more recently are actually farther in this notion. The notion is that inflammation enhances the efficacy of CFTR correctors, even though, of course, after, for example, Trikafta and so many other studies, and as you have alluded, the inflammatory status is not completely resolved, right? So my question to you is, can you comment on the notion that you have raised and so many others that because inflammation is still left, even though albeit at lower levels, it's important the use of anti-inflammatories. So my question is, if you give anti-inflammatories, how much are you going to be interfering with the enhanced efficacy of modulators? And therefore, is it good or is it bad?
Yeah, I have to say I've read your paper, very nice, actually. Yeah, there is a very intriguing question. It's not just a question; it's an intriguing new field that. The answer is that I don't know. We don't know how much should we treat, for how long, and what is the outcome would be. So I think it's really a new field of investigation. What we have studied inflammation and infection, I see like Emanuela behind you, it's completely different now. Like it's a different area. So yeah, I totally agree with you. It's intriguing the fact that inflammation makes the CFTR modulator work better. This is, if I don't remember, if I'm not wrong, there is this study. There are some studies that suggest that the inflammation actually lowers CFTR. So that's probably why the CFTR modulators work better, because they have a broader, a wider window of activity. But we don't know yet. I mean, I don't have a real answer for that. Just that we must continue to investigate this.
Obviously, I'm not going to be discussing here the discrepancies between studies, but again, more studies are coming out suggesting that. And so the point is perhaps that little bit of residual inflammation is actually good for
Good, yes, it's good for... I mean, inflammation shouldn't be abated. It should just be re-educated.
Yes. Antonio,
Antonio.
wonderful talk.
Thank you.
So what... when you are going to try those resolvins in patients,
okay,
and I saw that in some of the studies you are using resolving 1 or resolving 2. What is the difference, and how you are going to pick which resolving to use in patients? And in designing your experiment, based also on the discussion previous talk, your clinical trials, when do you think you should start with the treatment with the resolvins?
So I'm starting, if you don't mind, but with the second question, the difference between D1 and D2. They have different chemical structure and they bind different receptors. Again, in the poster, we showed that, for example, in primary cells, human cells with CF, RVD1 and RVD2, they have a completely different transcriptomic effect on cells. So they have a different mechanism, but the final result is essentially the same, lower the inflammation. So how would I pick? I don't have an answer for that too, I'm sorry. And for the clinical trial, I was asked this question last night by, I think it was Marcus Mal as well. And I said, I mean, I honestly don't have the capacity and the potential to do a clinical trial on resolving. So, I mean, I hope there will be a clinical trial on one of the resolving soon, but I don't know when. And when should we start our, I think it depends, it really depends on the patient. I think it depends if the patient already has some inflammation in the, even if they are young, or if they still have some residual, or how they are managing their overall lung condition, but is, I think that the treatment should be tailored on the patient somehow.
Are there already clinical trials?
There have been some clinical trials on Resolve, not on CF. I mean, at least for phase 1 assessing the safety, which was okay, and phase 2A, I don't remember what kind of disease was. I'm sorry.
It's okay. Perfect. Thank you so much.
Thank you so much.
You're very welcome.
We'll take some other questions at the end, if that's okay. All right, last we're going to bring up Dr. Katie Heisert from National Jewish, who is also an adult pulmonologist there. I'm excited to give her perspective on immune phenotyping as she talks about immune modulation to help control CF infections.
All right. Is it supposed to show up here? Oh, okay. Good morning. Thank you to the organizers for inviting me, and thank you to all of you for staying for the last talk of the last symposium. I am doing something a little different today, that this is more of an idea talk, and there's only 3 data slides in the entire talk. So hopefully people will have ideas and questions at the end. Let's see, the arrow key you said? Oh, okay. All right, these are my disclosures. And as Ben mentioned, I'm an adult pulmonologist, and that really informs how I think about my research. I look at my patients when I see them in clinic, I see what they're struggling with, and it really guides our studies of infection and inflammation in the lab. And so the premise for this talk is that, as has been brought up, CFTR modulators cannot reverse all pathology in people with CF, and therapies are still needed to treat non-resolving infections and deleterious inflammation. And I use the word deleterious inflammation. I really liked what Antonio just said, that we want to re-educate inflammation. We don't necessarily want to turn it off. We have to figure out what is deleterious and what is protective. So the observations that lead to some of the ideas in the talk today are that chronic infections may result from a failure to eradicate acute infections, and that lung damage may be amplified by aberrant and misdirected inflammatory responses. And so the question to be answered is, can we harness the immune system to help fight infections and reduce disease pathology and symptoms? So the outline for today, I will first talk about that we do know that immune cell plasticity can be harnessed, and then get into some of the challenges that we have faced in using immunomodulatory therapies in CF, with the stress on identifying new clinical endpoints and biomarkers, and then ideas for designing clinical trials to increase our ability to identify effective therapies. So to begin with, I'm going to tell you a story that really demonstrates how well immune cell plasticity can be harnessed therapeutically. This is a story that was published in the New England Journal in 2020. This is a case report, but I think it is very illustrative. So this is the story of a child who developed disseminated fungal infection with coccidioides. This is an infection that normally doesn't cause very severe infections in people. If they get an infection, you give an antifungal, it's cured. However, this child developed systemic disseminated fungal infection that was progressing despite maximal antifungal therapies. And when we see this kind of disseminated fungal infection, we usually only see it in people with very severe immune compromise. And this had been a previously healthy child. They ran all the clinical tests looking for some kind of immunodeficiency, and they didn't find anything. So they were completely perplexed. And someone had the idea to see if the child's immune system was actually responding in the right way to clear the infection. And they took out the child's T cells, and they found that he had an inappropriately Th2-dominated immune response. So to take you back, we've talked a little bit about lymphocytes, but as a reminder that CD4 T cells, or T helper cells, can develop different phenotypes that contribute to infection resolution and to disease. And there's many different types of T helper phenotypes, but for the sake of this talk, I'm going to mention 2. And if you have a naive CD4 Th0 cell and you expose it to products from macrophages, particularly IL-12, it will become a Th1 cell. This cell makes interferon gamma, which further amplifies its phenotype, and these are very important for killing intracellular pathogens or anything that's phagocytosed by a macrophage, and this is referred to as type 1 immunity. In contrast, if that Th0 is exposed to IL-4 that's made by eosinophils and mast cells, often during allergy, it will become a Th2 cell, which also makes IL-4, amplifies its own phenotype. And in addition to allergy, these are really important for parasites and extracellular pathogens like worms, and this is referred to as type 2 immunity. Very importantly, these two types of T cells can act antagonistically on each other, so interferon gamma turns off Th2 and IL-4 turns off Th1. And the clinicians treating this child thought maybe they could take advantage of this factor here. So they decided to enhance signals for Th1 and dampen signals for Th2. And you can see in the graph here, they started originally by giving interferon gamma. And there's Th1 and Th2 cells there, but there's no difference in the ratio of these cells following the interferon gamma injections. They then gave dupilumab. Now, this is an FDA-approved therapy we have for allergy that blocks IL-4 signals. And you can see that after they gave the dupilumab, the ratio of the cells changed and the number of Th2 cells came down. And this correlated with what they saw with disease. So this poor child had fungal infection intracranially and in his spine. And you can see that after the interferon gamma, the lesions around the skull and in the spine had only progressed. But after they gave dupilumab, the disease essentially was completely resolved, and this child was completely cured of his illness. And so why was this case successful? Well, first of all, they had knowledge of what the immune response was supposed to be to defend against that pathogen. They identified inappropriate immune skewing in the patient that had led to his susceptibility. They had targeted immune therapies to shift the cells available to them so they could shift to the necessary phenotype. And they had a very clear endpoint for determining success, which in this case was disease resolution. And what I would like to propose is that these are 4 critical components of successful immunomodulatory therapy. And if we want to proceed with therapies for our patients, we really need to hit each of these components. So we've actually been trying to use immunomodulatory therapy in CF for decades now. There's been a lot of clinical trials, but we've had a lot of challenges implementing any of these therapies. And so I can't talk about all of them today, but I want to talk about a few of them that have not proceeded. So we have tried nebulized interferon gamma in CF patients, and this was a clinical trial that the idea here, and this was mentioned earlier in the session, is that there has been a description of a Th2 immune phenotype in the airways of people with CF, but you need Th1 to clear Pseudomonas. And so the idea was, let's give interferon gamma, shift the immune response, and see if people do better. But this trial had to be stopped early because people receiving the interferon gamma were having more exacerbations than people receiving placebo. LTB4 was mentioned today. So this was another target that we tried to use in CF, using LTB4 inhibitors to block deleterious inflammation produced by neutrophils. But again, this trial was stopped early because people receiving the treatment were having more exacerbations than people receiving placebo. And then there's been quite a number of trials of anti-inflammatories, such as lenabosum, which is a cannabinoid 2 receptor agonist, which were safe, and the clinical trial went all the way through, but the primary endpoint did not show any difference between the placebo and the study drug, with maybe some mild secondary endpoints that reached significance. So why so many trials that haven't led to successful therapies? Well, I think we have gaps to fill. So particularly in CF, the lung is a spatially and immunologically complex organism. This is a problem in many lung diseases in terms of immunomodulatory therapies. And determining which responses are pathologic versus protective is essential. So when we think about the LTB4 inhibitors, some subsequent studies were done looking at the molecule they were testing in animals, and they found that when you gave the LTB4 inhibitors, you blocked neutrophils, but that actually led to overgrowth of Pseudomonas. So really distinguishing what's protective and what's pathologic is essential for knowing what's going to happen in the patient. And that gets all the more complicated because modeling chronic infection and inflammation is very hard in animal models. And that has really stymied our ability to study some of these processes. People with CF have varied manifestations of disease. Many of you have seen this in your patients. You can have the same genotype and people will have very different lung function, very different inflammation. This disease, we describe it as monogenetic, but we know there's environmental influences. We know there's other genetic influences, and one size might not fit all. We might need to immune phenotype our patients to figure out who's going to respond to the specific therapies. And then particularly for these inflammatory educating or anti-inflammatory therapies, coming up with an endpoint to determine efficacy is very challenging. We need to think about the length of the studies we're doing and whether we need new endpoints. So I want to delve into that last point in a little bit more detail about considering clinical endpoints when assessing anti-inflammatory therapies. First off, we often use exacerbations or time to exacerbation as an endpoint. But what is an exacerbation? I mean, I think a lot of us know it when we see it, and our patients know it when they are experiencing it, but it's defined as a period of increased systemic and pulmonary inflammation. And a lot of the criteria for diagnosing it are subjective. Our patients tell us, I'm feeling more tired, I'm making more sputum, the sputum's changed. And we have only a few objective measures, including change in FEV1. So let's think about that interferon gamma study, though. This is an immune stimulant. We're trying to shift the immune response and make it more type 1. Would we expect these people to have more or less inflammation in their lungs initially if we're achieving our goal? I've often wondered if they had pushed through the initial inflammation in these patients, would we have seen a beneficial effect? I totally understand why they stopped the study early, but perhaps we were looking at the wrong endpoint in this study. How long should trials be? Are we evaluating endpoints too soon? And should we be looking at FEV1 for an increase, or should we be looking for a slower decline in FEV1? And so particularly for anti-inflammatory therapies, I've drawn this little graph to demonstrate what I'm thinking here. We usually look at that yellow line, drug A. If we give the drug and there's the placebo on the bottom, you can see a huge effect at that first time point, and you'd be like, yes, this is a good therapy. But what if your therapy just slows decline of FEV1, which is very likely for something that's going to be modifying inflammation? If you look at that middle line, drug B, you'd have to go out for a long time before you might reach statistical significance, and even more so now with CFTR modulator therapy. So we really need to think about, is FEV1 going to be an endpoint we can really use? So that brings us to biomarkers, because ideally we would have biomarkers. We wouldn't have to go out quite as long in our studies. And here I just want to make another pitch about inflammation and re-educating that inflammation is not a monolith, that there's many different types of inflammation depending on the stimuli. We always think of IL-1 and neutrophil elastase in CF, and there's various things we look at, but most of these have not panned out as reliable biomarkers of inflammation in CF. Otherwise, we'd be using them clinically, and we can't seem to use them. So what I want to argue is that we should come up with better biomarkers, both for clinical use and for clinical trials. And I've been saying this for a number of years, some of you may have heard me talk about this, that I think using unbiased techniques like omics could really help us. And I think the omics field has really gotten to a point that we can apply it. It's a lot easier to use than it once was. So as an illustration of this, I'm going to show you a little bit of unpublished data. This paper was already mentioned today. I was very fortunate to be involved in this study with one center, multiple investigators of 12 patients with G551D mutations starting ivacaftor in 2013. And we collected a lot of specimens and we got a lot of data. And this was the main paper people like to talk about, but there was probably 10 papers that came out of this. One of them was a paper using proteomics to look at how the proteome of Pseudomonas changes in the airway before and after ivacaftor. So Xia Wu and Jim Bruce are proteomics experts at University of Washington, and I worked with Xia for weeks before we went to Dublin to come up with complicated ways to fractionate sputum so that we could get just the bacteria out of it at the end, and he could do proteomics on the bacteria. And this is a very interesting paper, if anyone hasn't read it, looking at how Pseudomonas changes based on its proteome in the airway, ex vivo Pseudomonas following ivacaftor. But we also did proteomics on the host, and I'm very sad to say we never got around to publishing that data, but I'm going to show you a little of that data today because I think it's a really good proof of principle. We took the sputum, and as I mentioned, we homogenized it and fractionated it. And so we had a supernatant and a pellet fraction, so a secreted and a cell cell fraction. And Shah did mass spec on these samples and identified the top 300 proteins. We applied a bunch of stringency parameters and then used statistics to figure out which ones correlated with changes in lung function. So what I'm going to show you here first is changes in sputum supernatant protein abundance at day 7, 1 week after ivacaftor, and how that correlates to changes in lung functions at 420 days, over a year later. So the top value here will be the R value, the correlation coefficient, and the bottom is the P value, or the significance. So we had tons of proteins, and I'm only showing you a fraction of them. But there's some usual suspects here, MUC5B, lysozyme, SLIPy. None of those, the usual suspects, had correlations. But then there's this protein DMBT1, deleted in malignant brain tumors 1, I'd never heard of it before, that had a very strong R and a very significant value with only 12 subjects. Now I'm going to show you the pellet, and that was even more striking. So this bottom protein, DAP12, had an R of -1, a perfect correlation, and an extraordinarily high statistical significance. Now, this is very preliminary data. This is 12 people. This is ivacaftor. It's not ETI. But it's just proof of principle that we came up with these two proteins, which then I went and looked in the literature, and they actually are associated with lung disease, just not CF. They had not been published on CF before, but other lung inflammation. And that these were things we never would have thought to look at as biomarkers of changes in lung function in people starting ivacaftor. And so I think that there's the potential for new biomarkers of inflammation that we can identify this way that could both help predict treatment response, which is what these biomarkers potentially are showing, and be used as endpoints in clinical trials of novel therapies. All right, and finally, for the last part of the talk, I'm going to talk about designing clinical trials in ways that may increase our ability to identify effective therapies. And now I do not do clinical trials, and I do not claim to know how to design clinical trials, but my proposal here is that we need to immune phenotype our patients, and that's an area in which I have more expertise. So if we go back to the 4 critical components, this brings us to number 2, which is about identifying patients who have an inappropriate immune skewing. And the story I want to tell you to illustrate this is the use of GM-CSF to boost macrophage killing of non-tuberculous mycobacteria. And some of you may have seen this paper from 2018, which was a case report in ERJ, where 2 people with CF with recalcitrant NTM, specifically M. abscessus lung infection, were given nebulized GM-CSF with benefits to their lung infection. I began thinking about that when I moved to National Jewish Health, which is, as I said, I went over to the dark side of NTM when I moved to National Jewish Health and thought it was really interesting. Why might GM-CSF be an effective therapy for M. abscessus? So NTM, opportunistic pathogen, you guys probably, just like Pseudomonas, breathed it in the shower this morning, but you will not get lung infection because the healthy lung does not get infected with NTM. And we think that's because you have multiple lines of defense. So here in this picture, you can see the first in the airway there, you have your epithelial cells with your mucociliary clearance. So that's your first line of defense, and things just get brushed out of the lung. But if you breathe very deep or have a very high inoculum, those bacteria are going to get down into the distal lung or the alveoli, where they're going to interact with those cells there, which are your resident airspace or alveolar macrophages. And these cells are thought to be particularly good at recognizing, ingesting, and killing bacteria without mounting a big inflammatory response. Otherwise, we would all have pneumonia all the time. So how does this differ in people with CF? Well, by definition, you have airway damage. We know that the mucociliary apparatus doesn't work as well in parts of your lungs. And we know that people make thick, viscous sputum, which blocks the airway. And blocking the airway does 2 things. It prevents the bacteria from getting to those resident cells, but it also traps the bacteria there in the airway. And there's a larger body of literature now, it keeps growing, that in CF and non-CF bronchiectasis and COPD, the cells that come to fight infection in the airway are not the resident cells, but in fact, they're recruited from the circulation. They're neutrophils and they're monocyte-derived macrophages. So now you have 2 different macrophages there, and they differ not only in origin, but also in terms of the maturation factors that they're exposed to, or the colony-stimulating factors. What makes the resident cells in the lung, the macrophages, unique in the entire human body is that they are matured and bathed in high concentrations of GM-CSF, or granulocyte macrophage colony-stimulating factor. And that's in contrast to cells coming out of the blood, where the primary maturation factor is monocyte colony stimulating factor. So thinking about this, my lab decided to ask a simple question. Does exposure to that high dose of GM-CSF boost macrophage ability to kill NTM? So we're using Mycobacterium abscessus. We took healthy donor blood, isolated the monocytes, matured them for 6 days to monocyte-derived macrophages using the established method, which is MCSF. But then we tweaked the protocol for the last 24 hours, and we changed the media to either have no GM-CSF, a low level that's thought to be in plasma, a higher level that's thought to be in the alveoli, or the sledgehammer dose that a lot of people use when they do in vitro experiments. We then infected with M. abscessus, and we determined colony-forming units at 1 hour after infection, which is time 0, or 4 days later. And what we found, here we have CFUs at time 0 on the y-axis and the different concentrations of GM-CSF on the x-axis, is that at low levels of GM-CSF, the macrophages are just terrible at killing M. abscessus. But when you ramp it up to levels you can see in the alveoli, the macrophages become very effective killing machines. And so the hypothesis we have moving forward and that my lab is studying now is that GM-CSF activates macrophages for effective NTM killing, and we're studying the mechanism of what that is, that insufficient GM-CSF signaling contributes to susceptibility to NTM infections, probably one of multiple factors, and that macrophages recruited to the airway are not exposed to sufficient GM-CSF to eradicate invading inhaled NTM. And we're using mouse models of airway infection as opposed to alveolar infection to look at this. So getting back to this type 1 versus type 2 immunity, is this a skewing? And I would argue that it is, that GM-CSF is associated with type 1 responses and MCSF is associated with type 2 responses. And here's a picture we took of M. abscessus bacillus and a mouse macrophage. These are intracellular pathogens. And so what you really need is that type 1 response. So there have been 2 clinical trials to try to do this, the first of which was in CF patients in the US, but had to be stopped early because it happened during COVID and right when modulators were introduced. But this is a study done in non-CF bronchiectasis. And the results, this is the abstract that's been published, and I can safely say that the full study is going to be published shortly, thankfully, because it's a really interesting study. They showed safety of the GM-CSF, but in their 32 adult patients, they didn't see a significant culture conversion rate when they looked at the cohort as an aggregate. But if some of the patients converted, some of the patients didn't. And so this is where I'm going to argue that heterogeneity of patient immune phenotypes will influence efficacy of our detected efficacy of our therapies in clinical trials. So if some people benefit and some don't, but you don't try to understand what makes those people special who benefited, you might be missing a therapy that you could apply to just a certain part of your population. And the reason I think this is particularly interesting for GM-CSF is because of this paper that came out of the Cincinnati and the Ohio State groups in 2022. They did bronchoscopy on people with CF with and without NTM lung infection, and well as some healthy controls. And they looked at 6 different regions of the lung, and they looked at immune cells and cytokines. And they were mostly focused on the immune cells, but what really interested me is they evaluated 45 different cytokines in those 6 regions of the lung. And what they found was that all cytokine levels were higher in the bronchoalveolar lavage fluid of subjects with NTM infection as compared to those who didn't have NTM infection. And the levels correlated with regions of increased lung damage. So that makes sense, right? You have more inflammation, more lung damage, and that's because you have an infection, except for 2 cytokines. GM-CSF and MCP1 were higher in the BAL subjects without NTM infection, which of course made me very happy because this supports my hypothesis. But what I really want to show you is the heat map of this data. So this is 2 of the 45 cytokines, IL-8 representing the majority and GM-CSF being the outlier. And you have people with CF on, with and without NTM on the y-axis there, the different regions of the lung across the top. Green is low, yellow is mean, red is high. And I'm not showing you the healthy controls here. And the 2 takeaway messages I want you to take from this plot is that on average, airway GM-CSF levels were higher in those patients with CF who didn't have NTM compared to those who did have NTM. And they actually had higher levels in the CF without NTM than the healthy controls. But really what I want you to look at is NTM positive patient number 1. there's heterogeneity here. That patient, number one, has high levels of GM-CSF. So if you treated this person with GM-CSF, I don't think they would have any benefit. They have some other reason they're susceptible to NTM, and they don't need more GM-CSF. And so I think that this is an example where immune phenotyping the population would really help us in our clinical trials to determine if GM-CSF is effective. So to end with, I think there's promise for successful immunomodulatory therapy for people with CF. In terms of the first point, the knowledge of the immune responses, I think there's evidence from here today and at this entire conference that there's really good ongoing host pathogen research into chronic infections, and we're making progress here, and we do understand what we think we need to help. Identifying inappropriate immune skewing, I think this is an area we need to do more of. I think we really need to figure out for these immune therapies, because of the heterogeneity of our patients, who's going to benefit. Because I think we're losing drugs in the clinical trials that may benefit a portion of our patients. We need targeted immune therapies to shift these cells, and the good news is a lot of these exist already in other diseases. They're already approved. And we need clear endpoints for determining success of therapies. This is another area where I worry that we've been testing drugs and maybe looking at the wrong endpoints, and maybe they're effective, but we've been throwing them away because we didn't know what our endpoint was supposed to be. With that, I want to acknowledge my lab, the people at National Jewish Health in Colorado who I've been working with, of course, all the great people at Seattle who I started working with, as well as people at other sites, particularly on the Dublin study. And I'm taking any questions.
Hi, Katie. That was a really cool talk. And I have kind of like two questions, but I don't really know the exact questions, so more like, would you comment on? So I have two things. So the first one, I love the concept of immunomodulation and how to train the immune system to do what you wanted it to do. So for RSV, there is some data that, like not in CF, but children that get, and maybe you have seen it in the clinic, that children that get RSV before, like everyone gets RSV before they are 5 years old, but there are some population of people that get RSV that it skews their immune responses to be more Th2 than Th1. So my first comment is that, do you see in these like people with CF that you're saying that they are already more skewed to Th2, that maybe they have gotten more viral or RSV infections? And like, I wonder now with the new RSV vaccine that if maybe RSV, it's like training your immune system in some point, that now that there is a new vaccine, maybe you wouldn't see that. So that's the first point. And the second point, it's that, so dendritic cells. So I remember from a very past life that I used to make dendritic cells, and we would add GM-CSF to dendritic cells. And some people have proposed to like do dendritic cell vaccines, right? So you like kind of like load them with whatever peptide and train them. So do you know like the main antigen for NTMs, and could you train your immune system to actually like, you could make like dendritic cell vaccines if you know the main like NTM antigen, so they would go and get into like the granulomas that were not?
Oh, I love these questions. I think they really shed light on the complexity of the situation. So in terms of like the Th2 skewing, I mean, there's actually data now that Pseudomonas itself can skew, chronic Pseudomonas can skew, and that I think just got published this summer. I think there's a lot of different factors. You know, this is the thing with a lot of clinical research. It's descriptive, right? They did bronchoscopies on these patients, and they just described that there seems to be more IL-4 and IL-13 and Th2 skewing in that direction. You know, how you get there is a great question, and I'm not sure we're going to be able to parse that out. You know, whether it's early viral infections, if it's the bacteria itself, if it's an effective CFTR dysfunction. All of these studies were done, you know, more than 10 years ago. So, and to vaccines, that is an area beyond my purview. I love the question. You're totally right. I mean, in vitro, we use GM-CSF and IL-4 to make dendritic cells. My theory has been, since all of our resident airspace macrophages are completely competent at destroying NTM on their own, that potentially you just need to skew the cell back. That is, all of, our lung cells do a fantastic job. So whether you need a vaccine or just to skew the cells back, I don't know. But hi, Robert.
Hello, Katie. Thank you for a provocative talk, as always. So I think immunophenotyping is a great idea because we really don't understand the biology of inflammation at all in CF, if we're honest. However, we do understand a lot of stuff about GM-CSF and its effects on neutrophils. So I would sort of provocatively say back to you that perhaps it's maybe not a great thing to give large amounts of GM-CSF to CF patients, as it will prime their neutrophils, it will cause their neutrophils to survive longer, it will cause neutrophil apoptosis, which is already delayed, to be even further delayed. So that could be a confounding factor.
So I will say to that, so that study I just showed, they do report safety. And then the Encore study, which was the US study that was stopped, Jerry, Nick, and I have all of the data from that. We need to write it up because it's a phase 1. It's about safety, and that was also found to be safe. So your point is very well taken, but I will say that from the actual practice so far, in terms of leading to increased inflammation and neutrophils getting out of control, we're not seeing that. So
I suppose what I'm saying as well, that could also be affecting your efficacy.
Okay.
Because you're not going to improve your lung damage if you're not having that pro-resolutory signal from your...
We'll give them GM-CSF and resolvins together.
Yeah, or just...
No, but your point is very well taken.
Block calprotectin. Talk about this.
Okay, right, yes, okay. Yes, we need to block calprotectin. That's very true.
Kate, thank you. That was an amazing talk. My question for you is, do we know that the monocytes macrophages that are in the lung of patients with CF have actually the receptor for the GM-CSF? Or because they are abnormal, we see some dysfunctional recruitment of several receptors on the plasma membrane of those cells. So, you can load the lungs with the GM-CSF,
right, but if they're not
cannot respond.
No, that's a very good point. So to answer this, we've definitely done this in mice, and obviously mice are not humans. I work alongside Kara Mold, who has done bronchoscopies on people who are healthy, and then she drops LPS into their lungs and causes a recruitment of cells. Believe it or not, people volunteer for this, and then she bronchs them again. So we have the single-cell RNA-seq data comparing resident and recruited macrophages. Or do you think it's the environment?
The RNA-seq will not tell you about a lot of things that are going on with receptor in the plasma membrane.
No, and that's true. And so one thing that comes up a lot in CF is are there cleavage, particularly of surface receptors? I have to remember if I've looked into the literature on the surface receptor, but it's a very good point. It is a concern that if the cells if they don't have the ability to respond, then they can't respond. So point well taken, yeah.
Jean-Marie from Montreal. I can tell you that there are some trials that did work, and we completed one, and we see an effect on overall the pulmonary function. No effect on. We tested a drug that helps resolution, and we see some effect on FEV1. A bit like you show the picture, like a small difference that develops over time. Only 6 months long, but you need more time to have a more differentiation. We measured numerous biomarkers, but weren't able to show something. Maybe we did not sample in the right place.
Right.
So I'm pretty sure that immunophenotyping could help this type to complement like an overall trial that includes a lot of heterogeneous patients.
Yeah, I mean, I think that in these studies where if there's a negative result, but some people sort of responded and others didn't, it may be worth, I mean, I don't do clinical trials, and so the ability to figure out how to do this, but then to go back and investigate the people who seem to responded and figure out what makes them unique. This is what happened in asthma, right? There were the non-responders, and they figured out it was actually a different cell population causing the asthma, and they came up with an entirely new therapy for people who had asthma caused by neutrophils instead of eosinophils, right? So we're a step behind some of these other diseases, and I think that we could make a lot of strides by learning from these other disciplines.
Yep.
Thank you.
Perhaps one last question, then people can come up afterwards to talk.
Hello, Mark Emenecker from University Hospital of Zurich and Basel and collaborator of Emanuela. First, a very illuminating talk. It was really nice. I I wanted to tell you that DAP12 has emerged as a very important target in Alzheimer's disease as well. It's been given a lot of attention because DAP12 is a receptor of TREM2, and TREM2 and ApoE4 are some of the most known risk factors of Alzheimer's disease. And if you need any reagents or contacts, I might be able to help you. I cannot promise, but we could talk.
No, that's great. And one of the things I saw, though I saw that, both proteins were associated with lung disease, DAP12 I noticed had been associated with macrophages, and that's near and dear to my heart, and I think it's the most important cell. So,
yes.
Excellent.
Please come up. We can, if the speakers don't mind, just waiting around for a few minutes if other questions come up. Thank you very much.